Шура, привет.
Я записываю.
Okay, you can share your screen and start now.
Um, so hello everyone. If everyone is here, I can start my presentation. Um, so I choose article about astronomy. It's it this article is Nature Astronomy journal, which called Nature Astronomy. This journal is
Show your screen, please.
uh, okay. So
Yeah, go ahead.
do you see my screen?
Yeah, go ahead.
So so this journal, Nature Astronomy, is a journal which considered in categories as a Q1 journal in the field of astronomy and astrophysics. So, and mm what is mean this title of this article? Resolved ALMA observation of water in the HL Tau disk. So it's interesting what is ALMA or what is HL tau and HL tau disk. So I will start um, giving definition of these terms. So firstly, ALMA, ALMA. So it's Atacama Large Millimeter Array, location in Chile, Atacama Desert. So this research was done using this ALMA, one of the most powerful telescope in the world. So this telescope is located high in the Atacama Desert in Chile, at about 5,000 meters above sea level. So it's a group of more than 60 radio antennas working together to study cold gas and dust in space. So ALMA is a joint project between Europe, the US, and Japan and Chile. So that's why its name appears in the article title, and it means the observation was made with that instrument. So in this slide, I um, I add some pictures of these uh, telescopes. You can see it. See it. So and next about HL Tau. It's young star in Taurus constellation. So HL Tau is a very young star, only about 1 million years old. So for us, 1 million years is not very young, but for astronomers, for scientists, it's not very big amount of years because they before this they have found more more old more older stars and planets, so that's why this 1 million years it's not big amount of um, year for stars. So and this star is located in Taurus constellation, which Taurus constellation, how we know it's considered like one of the constellation which which located in zodiac constellations. One of the zodiac constellation is Taurus constellation. So this HL Tau star is located in this constellation. I mean, so it Taurus constellation. It means which in Latin bull. It means bull. So and this HL Tau around of this the protoplanetary disk is located around this. So how we see in this picture. So and in this disk, gas and dust that are slowly forming new planets. So by this gas and dust, this planetary disk is forming. And this star system helps scientists understand how planets like our planet are born. So, if I describe this picture, um, here we see star, and around this, I mean, in orbit of this, some rings and some gaps. So, these rings, it's forming by gas and dusts, and in this dust, in these gaps, I mean, in empty places, there may be located some planets or some newborn planets, because um, these gases and dusts, by adding each other, they create some new planets, and these new planets wanted to clear their around, I mean, their orbits. So that's why here in this disk have some um, gaps, some empty places. So this disk is made with made from rings and some gaps. So next, and in this next slide, I add first page of this my chosen article. So here some review or abstract of this article. So what does what does it say to us? So what is there um, here said about water and their importance. Water is very important for forming planetary systems, and scientists used this telescope, which call it ALMA or ALMA, to study the protoplanetary disk around the young star HL Tau. So, and I also noticed about these names of this telescope and this star. So, ALMA, if we translate it, uh, so in Kazakh we have word alma. It's mean in English apple, and tau it's mean mountain. But it isn't related with this scientific article. But I noticed like this interesting fact. And next, they found about 3.7 Earth oceans of water vapor in the inner 17 astronomical units. So the study can only see disk's atmosphere because there is because um, there is a lot of dust, and H2 and oxygen 16 is the best tracker to show water vapor in the disk. So in this first page, in this review, says like this. So next, in next page, you can open it by your phone or mm, laptops, this second page of my article. So here said about water is one of the most important molecules in the universe, so it played a key role in the origin of life on earth. So scientists always look for water when studying other planets, and water exists in both gas and ice forms. Like other particles, there is a special region called the snow line where water changes from gas to ice. So, at the snow line, dust particles can easily stick together and grow into planet cores. So, how I said before, um, here in a disk have some rings and some gaps. So, in these gaps, here in these gaps created some planets, and very comfort place to creating snow planets, it's called snowline. So that's why this area is very important for planet formation. And water also changes the chemical balance of the disk because it carries most of the oxygen. So however, absorbing the snowline is difficult. It happens close to young star, and Earth's atmosphere absorbs water signals. Telescopes like Herschel, Spitzer, and other telescopes detected water before, but not clearly. So, in this study, scientists used the ALMA telescope to observe the young star HL Tauri. They found three clear water lines in its ink disk, its inner disk. I mean, the water emission is limited to a small gap, showing the first spatial image of water vapor in a planet forming region. This helps us understand how planets and water rich worlds like Earth area formed. So, in short, water is essential for planet formation, and this star, which called HL Tau disk, shows for the first time where water vapor is located inside a young planetary system. This helps scientists understand how planets are possible life can form in other parts of the universe. So, uh, next part of this article is called observation. So, here researchers observed the protoplanetary disk around HL Tau using ALMA telescope in Chile. They focused on three water lines in different frequencies at 183, 321, and 325 gigahertz, which trace water vapor at different temperatures and distance from the star. So the 183 gigahertz and 325 gigahertz lines show warm water outside the snow line, while 321 gigahertz line traces hot water closer to the star. So the data were preceded with the Gaza software, uh, revealing strong water emission centered on the dust peak. The study clearly shows that water vapor exists in the inner region of HL Tau's disk, providing key evidence of where water is located during planet formation. So, if it's not very understandable for you, I can introduce you with this table. So here explains more understandable. So, this table shows four water transitions observed in the HL Tau disk with ALMA. So, each row represents one molecular line at a scientific frequency, and this transition, rest frequency, and channel which flux mask radius, they mean. So, first transition. Transition shows the energy change in a water molecule. So, for example, in first row, pH2O, and here 3 in power of 13 and 2 in power of 20 means a para-water transition between two energy levels. So, and how we see here in first, second, and in 4, here started from P, but in third one started from O. It means para water and ortho water. So first, second, and fourth one is para water, and third one is ortho water. And what is mean? So it's their nuclear spin isomers, uh, and ortho it mean their spin's direction is like in one direction, and para it's opposite direction their spin. So, and about frequency, the observed signal, different frequencies trace different temperatures. So before this I set these numbers, so and it writing here. So, and in short, energy of the upper level. Higher values mean hotter regions. And in the next line strength, showing how strong the emission is. So water exists in two spin types. So how I said before, lower energy trace warm vapor is P, para water, and earth water, higher energy traces hotter inner regions. So their main water lines were detected in this 183, 221, 225 gigahertz, and the in fourth is a rare is a topologic and wasn't detected. So that's why we consider first three one. So in the next one, the spatial distribution of water vapor.
Okay.
So scientists studied where water vapor is located in the disk around the young star HL Tau. They compared two water emission lines. So they compared 183 gigahertz and 321 gigahertz. And in 183 gigahertz line traces cooler water spread further from the star, while the 321 gigahertz line traces hotter water close to the center. So this shows that the temperature decreases outward, forming a clear thermal gradient. Most water vapor lies in the warm upper layers of the disk. So, and the snow line, where water changes from gas to ice, is located at about um, 17 atomic unit from the star. So how we know one atomic unit? It's about 150 million kilometers. It means, and to find 17 atomic unit, we should multiply this to 17, and we will get very big distance. So it means most water vapor lies in the warm upper layers of the disk, and the snow line, where water changes from gas to ice, is located at about like this distance from this star. I mean, from HL Tau star. So here I want to introduce about table 2. So here, mm, one second, please. Table 2. Here, program ID, the unique ID of the ALMA observing program notes. It shows which research proposal the data came from, and different IDs mean different observing champaigns and lines, the specific water transitions. And each transition corresponds to a unique energy jump in the water molecule. P and O refer to a para water and ortho water, which differ by the spin of hydrogen nuclei. Both forms emit at slightly different frequencies, allowing scientists to trace water under different physical conditions, temperature, density, or something like that. And integration time, how long the telescope collected data for that transition. Longer time, better signal to notice richer and more accurate measurement. And PWV in millimeters, uh, it's the amount of water worth atmosphere during observation. Perceptible water vapor. So lower perceptible water vapor means clearer sky. So less interference from our own atmosphere. So end band pass or flux calibration, standard source used to calibrate the frequencies response and brightness scale of ALMA. They ensure that all measured intensities, and frequencies are physically correct. So, calibrators, nearby bright objects used to correct for phase variations, signal timing errors, so necessary for precise imaging and to avoid distortions in the disk map. So, and maximum baseline, the longest distance between ALMA antennas during that observation. The longer the baseline, the higher the spatial resolution, meaning how sharp the resulting image will be. So, from table 2, we see observations were made for both para and ortho lines, and the integration times ranged from 20, 31 to 100 minutes, showing varying depths and accuracy. Then the PWV values from zero point 0.2 to zero point 0.5 millimeter are very low, meaning excellent weather conditions and minimal atmospheric absorptions. And maximum vaselines varied from 500 to 8,547 meter. So longer baselines predicted higher resolution images, essential for resolving the fine disk structure and determining the precise location of water vapor. What this means scientifically, this table ensures that the water vapor detections in different frequencies are reliable and well calibrated. So differences in image resolution between the lines are explained by the baseline lens and observation setups, not by physical inconsistencies. By combining data from multiple programs, the researchers achieved both wide-scale coverage and high-resolution imaging. So, Table 2 provides the technical foundation for the entire analysis. It lists which water transition were observed, under what condition, and with what resolution. Although it doesn't directly show the spatial structure of water vapor, it explains why the 183 GHz and 321 GHz maps look different due to distinct observational setup and sensitivity. In short, this table guarantees that the following scientific results about the distribution and temperature of water vapor in the HL tau disk are based on high quality, well calibrated observations. So, and here, figure number 1, continuum and water vapor maps. So, this here we see panel A, B, and C. So about panel A, here 1.7 millimeter continuum and 183 gigahertz waterline. The left image shows the continuum map, the overall dust structure of the HL tau disk, and the medium image in the center image shows the integrated intensity of the 183 gigahertz water line, revealing where cold water vapor is distributed. So the right image shows the velocity map where the disk's rotation is clearly visible, proving that the water vapor follows the Keplerian motion of the disk. And panel B, 0.94 millimeter continuum and 325 gigahertz waterline, similar to panel A, but a higher frequency. And the emission here comes from warmer inner region of the disk. And the velocity map again shows clear rotation, confirming that the warmer water vapor is closer to the star. And in panel C, this panel 0.194 millimeter continuum and 321 gigahertz waterline. This panel focuses on the hottest and most compact water emission near the star, and the signal is weaker, so only the integrated intensity map is shown. On the right, zoomed in view displays the contours, clearly outlining the small region where this hot water vapor is detected. So these images show where and how water vapor is distributed in this HL tau disk, and the 183 gigahertz line traces colder outer gas, while the 321 and 325 gigahertz lines show hotter water close to the star. So the velocity maps also confirm that the gas is rotating with the disk. So, and here we show another figure number 2. Um, so panel A, 183 gigahertz waterline spectrum extracted from a circular area of radius zero point 0.7 centered on the continuum peak, shows broad emission around the systemic velocity 7.1 kilometers second. Panel B, 325 gigahertz line, same area, also shows a flipped mirrored version, dotted line for comparison. So, and panel C, 321 gigahertz line, but extracted from a much smaller circular region owing to higher resolution and lower SNR. What we learn from it? The spectra show that water lines are detected and centered at the system velocity, confirms they come from the disk, not some random interstellar cloud. The width of lines increased for the higher frequency transitions, and indicated emission comes from inner parts of the disk where orbital velocities are higher, and the smaller extraction region and weaker signal for the 321 gigahertz line reflects how the hotter water vapor is more compact and closer to the star. Why is matter? This figure supports earlier map, um, figure 1, by showing spectral evidence of water vapor in different disk regions, combining where and how fast the water is moving, including in it your not only do we see water in those rings, we also see the speed and region from its spectrum. So, water column density. It's our next part of this article. Uh, so, in this section, the scientists used the three main water lines to study the amount of physical condition of water vapor in the tau protoplanetary disk. The applied method called a rotational diagram, which helps determine both the temperature and column density, the total amount of water along the line of sight. To make this calculation, they assumed that the water emission is optically thin, meaning that light can pass through it easily, and that the excitation temperature, the temperature that defines how the molecules are distributed among energy levels, is uniform across all lines. However, later analysis showed that is assumption wasn't accurate, since the disk actually contains water at different temperatures in different regions. Temperature results two main layers. Using a Monte Carlo Markov chain statistical analysis, the team found two distinct temperature regimes, which together suggest a continuous temperature gradient within the disk. So, inline 183 gigahertz, lower energy temperature is approximately 214, and colder water vapor close to the snow surface where ice just starts to sublimate. And in 321 and 325 gigahertz higher energy, temperature is 789 Kelvin. Warm gas located in the inner upper layers of the disk near the planet forming regions. This clearly shows that the water isn't eventually heated. The temperature decreases with distance from the star, meaning the inner regions is hot while the outer region is cold and icy. The higher temperature component likely represents warm water vapor in the upper layers of the disk, while the lower temperature part tracks colder gas near the snow line, the region where water changes from ice to gas. I said about it. So, optical thickness and mass effects. So they also checked whether the emission may come from massing, which can artificially increase this flux. However, no narrow matter like spectral features were found in the this 183 gigahertz and 325 gigahertz lines. This means the emission is mainly thermal, not maser driven, and mostly optically seen, especially in the outer disk. Only the very inner part may be somewhat opaque. And water column density amount of vapor. From the rotational diagram, they estimated a total water column density of like logarithm 10 n sin divided by centimeter square, and it's equal to um, 16.441 within about 0.7 arc seconds. It's approximately 100 atomic units from the star. This corresponds to roughly 3.7 Earth oceans, or about 0.07 lunar mass of water vapor in total. So it means it's in this area 3.7 Earth oceans amount of water, but in form of gas. So, however, since most of these emissions originated from the inner 17 atomic units, actual concentration in that inner zone must be much higher, approximately um, 18.1 when corrected for disk insulination. This makes the measured value a strict lower limit, meaning there is at least that much, but possible much more water present. So H2 oxygen 18 not non-detection and optical depth. The researchers also searched for rare isotopic version of water to test the optical depth of the main lines. Since this isotopic version of water wasn't detected, it shows that the main water line, especially 325 gigahertz, isn't strongly optically thick. They calculated an optical depth is um, smaller than 14. This supports the idea that the emission mostly comes from optical thin regions and that the measured water amount is a reliable lower bound. So water to dust ratio and visibility. They compare the total matter mass and the amount of dust in the same region. The result gives a water to dust mass of a ratio of 6 minus 5 degree of 10. This is much lower than the typical value expected for inner disks. Such a low ratio suggests that ALMA only detected the upper, warm layers of the disk, while the deeper layers, where most of the water might be, are hidden behind the optically thick dust continuum. The dust is so dense that it blocks part of the water emission, especially near the midplane. Scientific meaning and implication. These results confirm that the three detected water lanes trace different regions and temperatures of the disk. Most of the water vapor lies in the upper warm layers above the snow surface. and the inner disk is partly hidden by thick dust, so ALMA can also see the top of the atmosphere-like region. And the non-detection of H2 oxygen 18 supports that the gas is only mildly optically thick, not dense enough to fully absorb the emission. Overall, the finding gives first first spatially and spectrally resolved measurement of water vapor in the HL tau disk. So, uh, and next part of this article is conclusion. Conclusion: all of these measurements. With the help of the ELMA telescope, scientists detected three water vapor lines in the inner part of the HL Tau protoplanetary disk. This is a big step because it's the first clear detection of water vapor so close to young star where planets are forming. Why it matters? It shows where and how much water exists in the disk, and it helps us understand how planets might get their water. Alma strengths, very sharp images, millimeter resolution, and high sensitivity, even at difficult frequencies. So, thanks to this, scientists could see where the water vapor is located and how warm it is. And main results, the signal come from warm gas in the upper layers of the disk, and these areas above the snow line where ice turns into vapor, into gas, temperature drops further from the star, and the radar isotope wasn't detected, and the ratio of water to dust is very low inside 17 atomic unit, showing that we mostly see the thin upper layer, not the dense bottom. In short, Alma sees water vapor high above the disk, while dust hides the deeper layers. And in conclusion, the study water in young planet forming disk, the best way is to observe the main H2O, I mean water lines in the millimeter range, especially inside the snow line where dust is thick. And about methods, target young star Achil Tau surrounded by a planet forming disk, and instruments ALMA array and observed water lines. It's uh, 183 gigahertz and 321 and 325 gigahertz, and extra lines H2 oxygen 18 at 322 gigahertz. Observation years is 2017, 2019, and 2022 using 40 and 50 antennas and baselines 15 meter to 8.5 kilometer. Um, and excellent, very dry air weather, and calibration data were corrected using bright stars like given here, and image resolutions and signal quality, measured water fluxes. I told about this, and also it written in this slide. So, and data processing and modeling. Spectral modeling, the 183 gigahertz water line was very clear. So scientists compared it with a Keplerian disk model. And radial distribution, the spatial distribution of water emission was modeled as a Gaussian profile. And rotational diagram, three mean water lines were analyzed assuming optical scene emissions. uh, and I said about optical depths before, and overall interpretation. This study is the first to map water vapor, water in form of gas, in detail inside a planet-forming disk. It shows that water vapor lies in warm upper layers of the disk. The lower layers contain water hidden by dust, and planets likely collect water from this warmer region. Alma's higher resolution data helps scientists understand how and where planets get their water. So it's my reflection and final thoughts about this article. And finally, HL Tau is not just a young star; it's a living laboratory showing how worlds like ours are born. And from this article, I realized one profound truth. Everything begins with water. The study reveals that water vapor isn't randomly placed, it's found in the warm upper layers, ready to become part of forming planets. This means that water isn't only vital for life, it's also the main storyteller of how life begins in the universe. To me, this research proves the power of human imagination combined with technology. Scientists have managed to see the motion of molecules in a disk hundreds of light years away, and that's absolutely mind blowing. And perhaps our own solar system once looked just like HL Tau. And so, when we look at this star, we are actually looking at the origin of ourselves, of our planets. So, thank you to attention. And if you have any questions, you can ask.
Can I ask question?
Yeah, of course.
Mm-hmm. Okay, yes, thank you, Dina, for your presentation. So my question is simply, but maybe interesting. Okay,
Mm-hmm.
why is water considered
Mm-hmm.
the key to planet and life formation?
So, how I said before in my conclusion, water is important. Is key because it helps planets form and life appear, and water ice helps dust stick together to make planets. How I said in Snowline, and by this created some gaps in disk, so it also cools or warms surfaces, transport materials, and always chemical reactions that life needs. Water, there could be condition. If there is water, there could be conditions for life. So that's why uh, water is key.
Mm-hmm.
So
Okay, thank you.
I want to continue the topic of water and ask you a question about if there is little water in HL tau, what will be the consequences of it?
yeah. So planets would grow slowly and stay small because of here little water, and planets will be dry without oceans or atmospheres. So like us, like our planets, and also water ice would only exist for far from the water decides how planets form and whether life can appear.
Thank you.
1, 2, 3. Okay, thank you, Dina, for your presentation. I have a question about your art- article. Nowadays, do scientists like explore new planets hoping to find or create some life?
No, science don't try to make life on other planets. Um, they want to understand our um, history, like ourselves, like how our planet and life formed, and also there these actions like preparing for the future. I mean, if our planet becomes unlivable, we know how life could survive elsewhere. So when they study water and when they study about this, they want to see the condition for life, not create it. So
Okay, like Elon Musk in the Mars. Yeah.
yeah.
Thank you. Thank you.
Okay, and I also have a question. How can this research inspire humanity or future space missions?
Can you repeat question, please?
How can this research inspire humanity or future space missions?
This research is inspiring because even A tiny drop of water in space tells a big story. It Scientists search for water and life on other planets, and it shows us we are explorers learning the universe history. Um, each discovery brings us closer to answering: Are we alone, or have other planets which have life there? So.
Okay, thanks.
I also have a question, and is it how the study changed your view of science or space?
Okay. Um, can you repeat this question, please?
Okay, how the study changed your view of science or space?
I used to think astronomy was just about stars and planets, but now I see it helps us understand our past and think about our future. Scientists aren't just looking, they are tracking the universe history drop by drop. Even small discoveries, how I said before, helps us understand how new planets form and how um, our planet got life. And so I now I see this by this article, by this study.
Thank you.
So, do you have another questions? If you don't have any question, else I finish my presentation.